Good morning, everyone. Monday morning, bytecode engineering. What could be more fun? Let's get started. Welcome, everyone. My name is Kees Jan Koster. I'm a Java engineer by trade. I'm married, 2 kids, live in Delft, Holland, and I ride motorcycle, although with this weather I decided to come by car. And I run javamonitor.com, which is the free online Java monitoring service for any JVM that you have. You can have a live demo there. What it does, it collects data on a central server and feeds you back things like memory use, database connection pools, give you an overview of your JVMs and how happy they are. You can share the information with your friends in a controlled way, so you decide who sees what data. And here's an example of memory use. This is a JVM that's fairly happy. And if you're hard at work, you can get SMS messages to warn you of problems. All right, but that's not what you guys are here for. You guys are here for JVM bytecode engineering, okay? Now I could bore you to death in about 20 minutes by going through the bytecode itself and talk about that. So I won't do that. That's a bad start of the week. So instead what I'll do is I'll mainly talk about the tool chain, about the JVM, and I'm trying to give you some examples with which you can get started with bytecode engineering. With those things in your hand, you can explore the bytecode instruction set yourself and you won't be bored. So that's a good thing. All right? If you have any questions, just ask. All right? Raise your hand, come forward, I don't know what, just ask your question. I like feedback from the audience. I know at DevOps is a bit hard because it's a huge room, but you're welcome to, please. All right, so here's what we're going to talk about. The workflow, the tools that you need if you want to do bytecode engineering. Bytecode engineering is not the happy ponyland that you're in when you're working with Java in a normal way. Right? So you need special tools, and this will give you an overview of those that are there. We'll look at the JVM architecture and where bytecode fits in. When you do stuff with bytecode, where that fits in. And I'll talk a bit about the instruction set. I'll give you some examples and show you some code. All right? One of the first questions that I usually get asked about this is, when do you use bytecode engineering? Right? When do you go down, open the hood, and look what's inside? And I think the proper answer is, you don't. There's no good reason to do that. All right? You can go your entire career and never ever look at bytecode, ever. And you'll be fine. That's good. That's okay. But if you're curious, or maybe you want to do something that Java doesn't permit you to do, then you need to open the covers, and then you can look in. And it's fun. It's not happy fun, but it's a learning experience. And they are fun afterwards. All right? Just remember that. I'll do a very quick example of something. I'm called in at customer sites to help out sometimes with performance problems, sometimes with problems coding. In this particular case, I had a problem of an application where database connections would go back into the pool and it would come out closed. So you have some code that opens the database connection, does stuff, and this is all framework, JBoss, this is massive dependency tree. And somebody somewhere is closing my transaction or my database connection, and I don't know who. Now, in my example code, you can just look at the code, and you can see where that database connection is being closed, right? That's the advantage of doing small examples. Is it possible to make that a bit more readable? I'm going to do a lot of code. The video is very hard to read in a room. And the sound is with echo, I'm told, but I'm afraid that's hard to fix. All right, so in my code, you can just see where the database connection is closed. But if you've got 25 frameworks managing your database connections, you can't. And especially if you're called into some strange customer site, you don't have access to all the source code probably. And then how do you find who closes the database connection? So what I'm going to do is I'm going to make a little tool that allows me to instrument a running JVM and to trap all the close methods on database connections, and that way I can see who closes my database connection. All right, just as an example of a use case that I've actually used in practice. All right, let's go back to the slides. Let's look at the JVM and the workflow a bit first. So this is the workflow that I personally use when I work with bytecode. Most of the stuff you want to do with bytecode, you can actually do in Java, right? It's just that there are a few details about it that you can't do in Java. So unlike Java code, you don't start with a clean slate. First, you write your thoughts in Java, right? Make a small program that does almost what you want, except that missing bit that you can't express in Java. Then you compile that code, run it, it won't work, and you decompile the code. You look at what the Java compiler made of it. And then from there, you enter the normal tweak, debug cycle, right? So instead, that bootstrap part that I call, usually that's Stack Overflow in Java, right? Type your problem in Stack Overflow, copy, paste, and then you tweak until it works, right? And here, what you do is you use different tools for that. Now, what happens when you look at the JVM? Why bytecode? How does that go into the system? And where do we tap into that? Here I show a JVM. I'm sure you've seen a picture like this one before. I show a JVM, and what you can see is the bytecode at the top. That's just bytes on disk in a jar file maybe, or on a network somewhere, or that's your application. That's your compiled class file. And that gets dragged into the JVM at some point. All of this code is loaded into the JVM. And it's first picked up by the verifier. The verifier protects the JVM from nasty code. It goes through your code and it checks for a few things. We'll see the verifier in action later. Okay? Then when the verifier is happy, the code passes on to the class loader. And the class loader will make an actual internal class representation of this. And then finally, classes, which you know, and objects, which you're familiar with, right? Even at the bytecode level, this is what you deal with. If we open up a class file, this is what it looks like. See the typical cafe baby? I'm told last week that the history of that word, cafe baby, is that the guys who made the JVM, the Java language, used to go to a cafe, and there would be a lady there. And that's the name for this tag. So what you see there is you've got the version number, stuff like that. This is what your class looks like on disk, right, when it's compiled into actual bytecode. And how many people here have done assembler programming? Anyone? That's a fair bit. Oh, that's good. About half of the room. Nice. So for the guys who've done assembler, if you see, you look, you can see that class info, fields, methods, attributes, these are all separate in a jar file. These are all separate in the class. If you're used to coding assembler, or maybe compiling from C, C++ to assembler, you see that all that information is lost in the transformation. You just have a bunch of operations. In Java, that's not the case. Your class is still present in the class file. And it's accessible at runtime, both for the JVM and for your code. Now, wouldn't it be nice if you could fiddle with this, right? You've got a class, and it does almost what you want, but not quite. In my case, it doesn't tell me where all the database connections are closed. That's the only thing I would like to add. So wouldn't it be nice if we had some way to put maybe an extra field in, add a logger somewhere, put some other stuff in, right? Not change the actual code, but just add some stuff. Luckily, the JVM allows me to do just that. As part of loading code, what I can do is I can institute a transformer. The transformer will pick up every single bytecode that comes by, and you can transform it. This is only one way of doing it, right? I mean, I could use the tools to compile an actual class file. But that's so much work that I'm not even going to talk about it. I'll probably do it later on in the talk when I do the demo code. But this is actually the most interesting use case, where you can take a running JVM and all the bytes, everything that gets loaded, all of Hibernate, all of Spring, all of everything gets loaded, and you get to fiddle with it. How cool is that? All right? If you look carefully, you can see that at the top, I've got the class bytes. Then there's a transformer, and it changed some of the bytes into something else. That's the red, marked in red on the screen. All right? That's what we're going to do. If you look at the class, it's not quite the same class anymore. There's a little thingy that hangs off it. And the objects also have little thingies hanging off them. That's the transformation I did. That's my code. That's been instrumented, added to the running class at runtime. How do you do that? That's cool. All right. Now, there are a lot of frameworks that you can use to do this kind of stuff. Don't worry. After this, I'll go into code, yeah? So then you can wake up. So this is all about instrumentation. You know, mostly what you do with this stuff is aspect-oriented programming. And nowadays, we do aspect-oriented programming with Spring, you know, by using annotations or Google Juice, or you use it at that end. And if you can do whatever you want to do by using those annotations, that configuration, that's fine. And it's probably the easiest way, and probably the safest way as well. Then there's aspect J, which I'm not going to talk about. I dabbled with it, but I think Spring is a lot easier to use for the same. Java Assist, which I'll demonstrate here in the demo. GClib, which I've never worked with. BCL, I've done a lot with BCL, so I'll talk a lot about BCL, but the project is, as far as I can see, essentially dead. So instead, you should move to ASM. ASM is the most active library for bytecode engineering. All right? So don't take it from me. Look for it for yourself, but all right, now we're getting boring stuff. What I'll do is I'll do a real brief demo of the use case, and then I'll go into code so I can show you how I can trip these closed methods. All right? So this is a simple JSP page, which could be a bit more readable. And then if I run that, I'll run it here. It simply prints this information out, which was taken from a database. Actually hard-coded, but for the demo it's fine. Okay, so when the page gets loaded, at some point the database connection is being closed, and I want to trap that. I want to see who closed my database connection. All right. Let's see where I am. Yeah, this is the right class. Is this readable? No, it's not. Can anybody help me? Where do I increase the font size? Because this is not going to work. Can I just do this? Command plus. No! Doesn't work, doesn't work. Focus. I should have prepared this, shouldn't I? Font. You just need to speak up, guys, because it's really quiet here. Edit. Here. Is this the right one? 14? 18? Yeah. Oh, yeah. You can actually read this. Nice. All right. So, is everybody clear what we're going to do now? I'm going to make a class file transformer that's going to sit inside the JVM, fiddle with the bytes. All right? That's what we're going to do here. I'm going to do the same thing 3 times. Once with Java Assist, once with BCL, and once with ASM. Just to give you a feel of the tools and how they're used. All right? Java Assist is actually cheating. We're doing bytecode engineering, but not really. It's like swimming with dry hair. You don't have to actually use bytecode. All right? But this is just to get you started with how that works with transformers. At some point, I think it was with Java 5, Sun introduced something that they call the instrumentation API. And that's a very interesting API if you want to fiddle with stuff, because what it allows you to do, it allows you to actually introduce code into the JVM before the main method is started, and you can be part of the runtime. You can be part of the verifier class loader game. Everybody always told you that the main method is the first method to actually be called. But that's a lie. It's actually possible to have pre-main methods. There you go, at the bottom. What's a pre-main method? Well, what's in a name? A pre-main method is started before the main method. What you do at the JVM command line, which you'll see in a minute, I can specify before running the main, I want you to load this agent. It's called an agent. And that agent lives inside the JVM and it does stuff for me. In this case, transform stuff. Pre-main methods take as an argument an agent argument, which is for configuration, and the actual instrumentation API. Right? And what you'll see me do a lot in this kind of code is a lot of print statements, because I'm really paranoid. One of the problems with the instrumentation API, it's not very well used. And that means that little things like error handling are really weird. And if you make mistakes, the JVM will either just crash and die, SIG bus, no JVM anymore, or it'll not tell you anything but not load your code, or run some of it but not all of it. So over time I've gotten so paranoid, essentially everything you do, you print out saying, oh, now I'm here, hey, I'm still alive, this is working, I've tried this and it worked, I tried this and it didn't work. I advise you to do the same. When you're working with this kind of stuff, make sure you log everything. Don't worry about performance. All right? Just know that it works. So here what we do, in the pre-main method, all we want to do is register ourselves as a transformer. We want to have access to all the bytes. That's what we say here. And that's this little line here. Instrumentation.addTransformer. Add transformer allows me to put a new transformer in. You can have any number of these. And then, as a transformer, I have to implement this, a transform method. Woohoo! At least the naming is useful. So the transform method, if you look at it carefully, you can see outcome bytes in Go class bytes, also bytes. So this transformer method, when is it called? What is it for? This transformer method is called for every single class that is loaded after you've been instantiated. All right? So I register a transformer, and after that everything comes by. All of Hibernate, every individual Tomcat class, runtime libraries, the lot of it. Everything is first given to me. Here is a bytecode of a certain class. Do you want to do anything with it? No? Okay, I'll load it. Yes, here, give me the changed version, I'll load it. And your job as a transformer is to either return what was given to you or instrument it and then return it. What you've got to return here, what the return value is the bytes in proper order of a valid class, and then the JVM will load it for you. All right? So we need to make some form of class. Now, speaking of paranoia again, what happens is everything comes by. So in the first few runs, I was instrumenting the com.apple classes on my Mac, and it leads to really weird behavior. Nothing works, everything crashes, everything gives weird messages. So I ended up with this, where you switch on the class name, and only if it exactly matches whatever it is that I want to change, then I touch the bytes, otherwise, no way, no touchy. All right? Note also, by the way, again, you're not safe Java land here, you're inside the JVM, so things are a little different. Class names are represented by internal names, not by the class names that you guys are used to. This is how a class is called internally. Yes, question? Good question. So the question is, are things like the string class loaded before you get to this code? The answer is yes, it's loaded before you are, because, for example, you need string to do this match. So while not all of the JVM at this point is loaded, you see a lot of system classes come by. Particular string, I mean, this question was asked in a previous run of this presentation first. No, string not. So you can't fiddle with string. As much as I would love to, if you want to fiddle with string, what you do is you have to unzip the runtime jar, pick out the string class, and replace it with your own, which after this presentation you'll have the tools to do. And then, you know, then this seems safe. I can tell you that. All right, so I pick out the class. In this case, I have a pooled statement that is my class. That's the one that I want to check the close method on. And that class I'm going to instrument. All right? So far, this is all legal Java. It's simple. It's plain. This is just standard stuff. You know, bytecode transformers in the JVM. You'll do it after this talk. Don't worry. Now we get into the actual fiddling with bytes. I'll switch to a little bit of a different tack here now, just to give you a bit of a feel. Yes, this is the screen I'm looking for. Can you all read that? Yeah. Wait. Is that readable from the back? You're so far away I can't even hear you say yes. Anyway, what we're going to do now is we're going to look at bytecode, right? Just to get a feel for what bytecode looks like. And to wake up, probably, because you guys are very quiet. Bytecode is fairly hard to read. I mean, if I do more hello.java, it's easy. This is readable, yeah? However, if I do this, hello.class, which is the compiled version of it, uh-oh. See it anyway, of course. I mean, that's what we're here for, yeah? Oh. Yes. That's not very useful. You know, they say code is read more than it's written. Well, we better have some good tools to read this. Now, there's one little tool that in itself isn't very useful. That's called JavaP. That's the bytecode decompiler. What's nice about JavaP is that it's always there. It's like VI. It's completely useless, and you every time you use it, you hate it, but it's always there. Okay? So JavaP, you want to use JavaP. JavaP. It's part of the JDK. Minus verbose, because otherwise it's really useless. Hello.class. I never know whether I should give it the class or not. Okay. So this is the command line I typed. JavaP hello.class. And it just dumps, this is the code you've given me. Let's look at the structure of it. Public class hello. Constant pool, we'll get to that in a minute. Public hello. Main, haha, there we are. This is the main class. For the guys who've done assembler here, look at this information that's here. You've got local variable tables, you've got all kinds of stuff, you've got stack sizes, all kinds of stuff that's actually Java. So you've got a lot more information here than you did when you did the same thing for actual bytecode on the machine, so machine code. Assembler code is very flat. It doesn't have very much structure other than there's a next instruction after. But class files still have all the structure present. All right, let's go through this code. So bytecode looks a lot like assembler if you're used to using assembler. It's essentially a mnemonic, an instruction if you will, with an argument or 2 or 3 arguments. Right? That's all there's to it. And then there's a lot of that. Get static. So we get something of static. And luckily, whoever wrote JavaP was used to not having information, so they added a lot of documentation. And it generates here, oh, that static that we get is system.out. We load a constant, LDC, load constant, number 22, which turns out to be the string hello world. And then we invoke a virtual method. Which would that be? Oh, that would be println. Interesting. So this is hello world in bytecode. The arguments given are almost all references, the hash says it's a reference, into the big constant pool, which is a massive thing. You don't want to write this by hand. Good luck to you if you do. Some of it we can pick out, like here, number 22. That's the string we had. And here, print stream on system.out. Right? So how does that work? I mean, now I've got a lot of bytecode, and how does invoke virtual know to use the other stuff, right? Because we're not giving it, as we would in Java, the string. This is for the people who don't do assembler. All right, I made a slide to show you what happens here. What we're going to do is we're going to add the values 1 and 2 together, which should leave us with a value of, yes, 3. Good thing. How does it work? Well, the JVM is a stack machine. You can tell if you look at the instruction set, if you look at the whole thing, the guys who made the JVM were actually Sun Spark engineers. It has to be. There's a lot of stuff in there. If you read the instruction set and you know Spark assembler, you'll be, hey, that's strange. They did the same trick here and there. So if they weren't the same guys, they talked a lot. They shared a coffee table, I can tell you that. So the JVM internally is actually a stack machine. It's completely different from what you look at in a Java syntax. It's a stack machine, and on the right, you see a little stack that has some stuff on it that doesn't really matter what it is now. And to add the values 1 and 2, what we're going to do is we're going to push those values onto the stack, and then we're going to see what the add method does, the add instruction. There's our instruction pointer. That just goes through the bytecode step by step, each of the instructions. All right, so we push the value of 1 onto the stack. We push the value of 2 onto the stack. And then we've got the add instruction, which takes 2 values off the stack and puts the result, or the sum in this case, back. This is what the JVM does for a living. Okay? Cool slide, huh? It was fun to make. Interesting. Note it says I add. It sounds like it's typed. If you do assembler, if you do machine code, there is some typing, you know, those 64-bit, 32-bit, you've got stuff like that. But this is the Java type, integer. The instruction set of the JVM is actually typed. Even on this level, the typing is still there. And it's also where the verifier comes in. Because if I would have said push 1, then push a reference to hello world, the verifier would have said, hey, you're trying to add a string to an integer, and this is not Visual Basic. So it wouldn't have loaded the code. All right? Just for laughs, have you ever tried switching your language if you do 1 written out as a string plus 2 as a value in Visual Basic? Have you tried that? It actually adds 1 and 2. The result is 3. The worst is if you switch your machine language to Dutch, it won't work anymore because 1 in Dutch is meaningless. So, anyway, side story. True story. So, for the people who've used to using assembler, you don't have all the freedom that you have with assembler. In assembler, what you can do is you can take anything, give it to the machine, and it'll just start executing it. And it's perfectly happy to do so. In Java, not so. The JVM will actually check before the code is loaded into the JVM, it'll actually check that this typing at this level is correct. You cannot add a string to an integer in Java. And that's also, this is also part of design to make it safe against stack overflow attacks or against stuff like that. Yeah? The idea was to have loadable code that you're not quite sure what the origin is, and then safely run that inside the JVM. And that's the kind of stuff you need to do at this level. Of course. Yes. All right, so the question is, in this case, it's fairly, well, it's blindingly obvious what's on the stack. So how, does the verifier always verify this all the time? Well, the stack use of each instruction is known. It's documented as part of the instruction. So yes, the verifier actually goes through all of your code and does its best. I mean, I'm sure you can construct cases where it won't work, but it does its best to verify all of it. And it's pretty good. Okay? So you can't just put random instructions in order. They have to be on the stack, they have to be compatible in typing. Okay? Most instructions are typed. There are a few things like duplication, where you take the value of a stack and clone it into a second one. Those things are not typed. But everything that has to do with arithmetic or objects, yes, objects even, yes, they are typed. Okay? And checked by the verifier. Sorry. That means not too much hacking. All right, let's review this code again. Get static. Nobody asked, but where does it get to? It's nice it gets it, but then what? Where does it put it? We don't have registers as we do on an actual CPU. Okay, so we don't have accumulators or anything like that. It's only the stack. So we get a static which is put onto the stack. Then we load a constant which is put onto the stack on top of that. And then we invoke a method which takes the information off the stack and puts the resultant back. In this case, as is very clear from this notation, it returns a void. So nothing is put back. And then we return. End of main method. JVM sees it exit, so there we exit. Cool, huh? So this is actual bytecode. Bytecode that you can load into the system. Let's return to our demo here. Those instructions are encoded into bytes on disk. I mean, they have to be stored in disk. If I want to do bytecode engineering, if I want to look at code, how do I do that from my own code? That's pretty tricky. Because all I have is a bunch of bytes. And this is where the frameworks come in that you use to actually do the bytecode engineering with. What you'll see with Java Assist, BCL, and ASM, those are the three I'll be using, is they all have a way to take the bytecode and to make an internal class representation. And to confuse things, this is not the class representation that you've been working with in Java. It's the same class, yes, and it's the same thing that you're talking about, but it's not the same representation. It's another set of glasses on the same bytes. And in this case, what we need to do is we need to make it a CT class. Don't ask what CT is, but the CT class is the Java Assist internal representation of a class. And here you can see how we transform the bytes into, this is essentially a class loader, except not one that'll run the class that we can instantiate objects for. And what's this mess here? Class loaders. The problem is, you live in a world where nothing is loaded yet. Pre-main, remember? You're on your own. You're in the system class loader. You're in the lowest class loader there is. You have no access to anything. You cannot instantiate a database connection pool object because you don't have that code in your class loader. That's loaded in a different class loader that you don't have access to. When I first did this code, I was instrumenting a Tomcat application. Well, Tomcat, at this point, isn't loaded yet. So how, if a Tomcat class comes by, can I instantiate that thing? There is no Tomcat. I don't have access. So what we do here is we make a really terrible link from the Tomcat class loader to our own. And we're going to say, oh, you'd use that class loader. And here, we create a memory leak because we never break that link anymore. So this is not code you want to use in production, but it works for demos at conferences. I've never understood class loading. Again, Kees Jan is paranoid. Print, hey, we found the class. And then we go through the declared behaviors of that class, so we now have an object that we can reason about, and it has methods. Woohoo! We go through the methods until we find one that matches the name that we thought was interesting. Remember, the close method. We want to instrument the close method. Okay. All right, now it gets dirty. So now I've found a method that I want to instrument. How do I instrument it? What does this look like to you? To me, it looks like somebody's trying to write Java in a string. Good thing. Java in a string. Who thought of that? So what Java Assist allows me to do, it allows me to sort of skirt by bytecode engineering by not writing bytecode. Instead, I can make these little strings of Java source code, and it'll compile them for me into bytecode. So I don't have to know the actual instruction set. I can still fiddle with methods. I can do this. If the method is empty, I'll set the body to be this code, which Java Assist will compile for me. Or, if the actual method exists, I can insert before. What do I do here? I create a new throwable, and I call e.printStackTrace. I call printStackTrace on that throwable. So I instantiate a throwable, printStackTrace. Right? So if ever this method is hit in the code, the effect will be on system out, there'll be, or system error actually, there'll be a stack trace. Which is what we want, because the stack trace will then tell me who closed the connection. Which is not what you want if you've got 1 million connections per second, but, you know, this is debug code. And finally, the new version of the class, we return as bytes. So we take the internal Java Assist representation of the class, and we extract the bytes again, which we then feed into the JVM. And this is the instrumented class. And if anything goes wrong or anything doesn't look like what we want to, we return the original class bytes to avoid crashing the JVM. And crashing here means crash and burn. You know, no stack traces, no nothing, just SIGBUS, we're done. Is this clear? Any questions about this? What's the class.detach is the question. Where is it? Finally, oh yeah. This is an attempt to break that nasty class loader problem that I've created just over. And it doesn't actually work. So this removes the heap memory leak that's also present, if that's any help. Okay? Yes? That's a good question. So if I load a class, we already start executing code. Yes. What's your question? All right. So the question is, if I load an actual implementation of a class into a class loader, it'll start executing the static block. Remember? That stuff you're not supposed to use? How does that work? Well, we, at this point, are pre that process. The code for that static block and the whole class actually hasn't passed into the verifier yet. It's not running in the JVM. That is why this class representation that we make here is different from the class representation inside the JVM. This is just an interface onto that byte array, right? For the purpose of changing that byte array. The actual class is not loaded until after we've returned the instrumented version, and that one will get loaded, and that's the normal JVM class loader, and that knows how to execute the static method. Okay? If you want to instrument the static method, so not a normal method, but a static one, you can actually get that. So this class, I don't know what it's called, but this class will expose a method that you can get access to the bytes of that static block. Yes? Who watches the watchman? Who loads the class loader class? Well, the JVM does. But by the time our pre-main runs, the class loader class is already there. Another question. Is the pre-main executed before the verifier? No, this code that I'm writing here passes into the JVM through the verifier into the class loader, right? So the game is not broken. You still have to write valid Java at this point.
Is there some, how can I see which classes of the standard library are loaded before this point and which one are loaded after this point?
Okay, the question is, how can I see which classes are loaded before this point and which ones are loaded after this point? I don't know. What I might do is I would log, because I did that a few times, just log every single class that's loaded. And that's a lot, I can tell you that. And then the ones that are not in there but do work must have been loaded before you were. Yeah, this is not the pony world. You've got to make do. One last question, then I'll move on. Yes? Are classes that are not used also loaded? As long as a class is referenced, maybe it's not instantiated, but referenced from another class, it is always loaded because it's needed for the dependency and for the verifier. But if you have maybe test code that is not instantiated at all, then no, it won't pass through the transformer. Right? This is an on-demand thing. I was going to say last, but one more then. All right, so suppose you've got several agents. Look, I'm just doing one. I'm paranoid enough as it is. I think you have to tread very carefully and use a lot of logging, and then you'll find out, because I really don't know. All right? But yeah, I mean, if you load a debugger, you've got a profile running, you've got, I don't know, New Relic, JRebel, everything running, you've got 5, 6 agents, and then you come along, oh, I'll introduce my own. Good luck. That's the fun of it, that's, it's racing with no helmet on. All right, so what we're going to do now is we're going to compile this, and I'm going to put that into my Tomcat, and I'll show you that it works. All right? No trickery. Although I need to find the right screens for everything. Wait, I need to increase the font a bit. All right. So what I do, I pack everything into a jar file named an agent jar. The agent jar, I told you earlier that you're in the base class loader, yeah? You are in a world where that's not quite complete. That's not ready yet. There's no Tomcat, there's no the safety of the frameworks you're used to. There's not even log4j. How can you live? So the problem also is that you get really nasty versioning issues if you start loading classes at this point from other jar files, especially from ones that you are also going to use in your application. It just gets really messy. So what I do to avoid some of that is I unpack all of the jar files as libraries, and I just dump all of that into the agent class. So the agent class doesn't depend on anything but itself, and all the code is right there. Right? I didn't even try to figure out how to load code from other jar files from an agent, because what you get is you need absolute paths, which are different on different machines, and it's just, I don't know what Sun was thinking. An important thing to look at is the manifest file. Come on. Manifest. All right, the manifest file is a beautiful piece of engineering. What you do here in the manifest file, you're used to saying, all right, main method is this. So you can say java minus jar, that jar, and it'll run the jar, run the main method. So the manifest file is a lot like that for the agent, but then you specify pre-main class. And it took me a while to figure out how to do comments in this file, and that's why prepending the word comment, because it doesn't know comment and it'll ignore it. Well, it won't ignore it, it'll bitch about the fact that there are 2 comments. But don't leave a space after tripwire, right? In one of my earlier implementations, you can't actually see it, but there's a space there. It won't work. And it won't tell you why not. And you'll rip your hair out. Why does line 1 work and 2 doesn't? Somebody kill me now. Right? So I told you now, don't do that. So what you do is you make a manifest file, and you put that in the jar file with the agent with all the code you need, and that's it. Reflection is your friend. Load everything through reflection, and then you can access it. All right, manifest. What I do in the build file is not very, I built that jar file. There we go. Build.sh. So this gives me a jar file that has the agent, has the transformer and everything it needs, and JavaSys in there. Now we need to tell Tomcat that we want to run this beast. Slightly larger font and VI. What I'll do, I put 2 Java options. This is just, I use this script always, so it's a bit convoluted, but in essence you type Java minus agent, etc. Okay? And the script just wants a different syntax. Here I say minus Java agent, and then you give it the jar file. That's the agent that gets loaded before the main method. Now the verifier, there are actually, in the newer JVMs, there are 2 verifiers. One that allows me to run my code and one that doesn't. I haven't looked in it any deeper, but this is the old verifier. So what I do now is I changed my JVM to use an older version of a verifier that's happy with the class format I'm making. I think if you use ASM, you can get around this problem because they've actually solved it. JavaSys and BCL trail a bit behind this and they haven't actually solved it. That's my understanding. But I'm afraid you're going to have to do your own research here. So what I do is I switch the JVM to the old verifier, and I say, all right, Java agent, my code. And I'm going to start my Tomcat again. Woohoo! It's alive! Yes, it did start. All right? If it didn't, where would you look? So now, what you can see is it started, but it didn't do anything else. It just says server startup. What happened to my transformer? Well, to get back to the question about unloaded classes, I haven't actually loaded the JSP yet. So the actual class I'm looking for hasn't been brought into memory yet. Like I said, it's an on-demand thing. If I refresh the screen here, this is my web app, refresh, it now compiles the code. Whoa, what's this? Well, that's actually what we wanted. First it says, hey, I'm instrumenting this thing, and the close method was empty. And now I put a body on it. Okay? So I know my code has been instrumented. So whatever is running as a connection pool is no longer the pool that was coded by the original author. It's that plus my little tinkerings on that. And at the same time, then there's this exception stack trace, which gives me beautiful insight in how a JSP is handled in Tomcat. So now I can see who closed my connection and why. Ta-da! This is where you clap. Thank you. Thank you. All right. So what have we done? We've made an agent. We've loaded it into the JVM. The JVM picked it up. Then as soon as a suitable class came by, we instrumented that class, and that class was loaded in the JVM. And that is generating this stack trace for me to analyze the problem I had. Is that clear? Cool. Now if I refresh that page, what you'll see is that I'll do get the... Hello? Are you refreshing? I do get the exception again, but it doesn't repeat the instrumenting this class. You know, it's just another instance of this happening. The code is just touched again. Instrumentation is only done on the first invocation. All right? Cool. So far we've used JavaSys, which is really cheating. I mean, if you're going to do bytecode engineering, do bytecode engineering. All right? This is just a way to get you started with agents and tinkering with classes at runtime. Let's do the same with BCL. Any questions so far? 2, 3, I'll start there. That was asked at JFall as well. Can you debug the tripwire application? I haven't tried, and I worry a bit. I don't think so, because we're not in the normal flow of things. I think the debugger will actually get the class wrong, because it probably loads the class from the jar file, and then I've got my instrumented class, which might confuse the debugger. So I think it's an interesting exercise, but I have very little hope it'll work. It does? Oh, you've tried it?
I tried to fiddle, and if you don't put some line mappings in, you get to the right line.
Ah, okay. So another gentleman comments that he tried it, and it does actually work because the line mappings in the class are actually correct. Right? Okay. Thank you. Same question. Wow, cool. I'm impressed. That actually works. Now, if I were to use a debugger ever, I might start using it. All right, now we're going to do the same thing. So you know what's going to happen, except we're going to take one step deeper into the water. We're going to switch to BCL. BCL is a bytecode engineering library. It's a fairly simple library that allows you to do bytecode engineering. What's in a name? And this you're now familiar with. We are going to be a class file transformer. We've got a pre-main, which in this case says we're instrumenting using BCL. We register ourselves as a transformer. It's almost cut and paste, isn't it? And we do the checking. We don't want to touch the classes. Yeah, we know all that. Again, first thing we need to do is get ourselves a representation of the class to fiddle with. And again, the tools are there. Java class, it's called this time. And we use a class parser. We don't have to do any nasty linking to class loaders for this. And then this thing, they don't call the things declared behaviors, but methods. Okay, so we iterate over the methods until we find the one that is named as the one that we are interested in, and then we're going to generate a new class. This is not JavaSys anymore. Inside the API, it managed the unlinking to the class loader. Well, what happens here actually, from what I understand, is they don't need to load the class. So all you get is a representation of the bytes that you're dealing with, and any dependent classes you don't have access to. So you don't need the class loader. Okay, so this is more low level. What we have here is we need to make an instruction list. An instruction list is what Java P gave us, the list of instructions that will be executed, and we've got to actually construct individual bytecode operations. And that's why this code is a bit convoluted, because, well, you've got to create a new, which is essentially saying, I want a new object of type string builder. I need to duplicate that, then I need to init that. Init, this is the internal name for a constructor. Append, put all kinds of stuff together. And then, finally, we call a toString on that. So this block, the only thing it does, it constructs a string that will be given to a throwable later on. Remember that if you look at the stack traces, there's this. I use the string tripwire in bold, so I can easily find that using grep. And I use the class name, just so that I really know for sure where I am. Making this string is done using this code. What we do is we create a string builder, and then we call append a few times. And here you can see how that is done. And then we create a new throwable, which we then initialize. We call a constructor on. And this constructor actually picks up one string from the stack, which was left there by the two. Actually, no, what it does here, we do a toString, which leaves it on the stack, and then we do a create store. Create store, what it does, it takes the value of the stack and puts it into a local variable. In this case, variable number 1. Good luck. And then here, we pick that variable up from the stack, from the local variable, and put it on the stack to be present for the print stack trace, for the init and later print stack trace. Is this clear? It's clear what's happening here. What I'm literally doing is I'm making a list of instructions that represent the code that needs to be run. Earlier in Java sys, that was just that string with Java syntax. Yep, I can scroll. So what you see here, for example, is the typing that goes in and out, and the invoke virtual instruction, the actual instruction here. And then what you do is you insert that instruction list. You insert it into the body of the method. So whatever is there, you put your list at the front. And then we start filling with stack and max locals. What's that? It's interesting because I've seen that also somewhere else. Let me see here. What's this? So I told you that the verifier goes through your code and it checks a lot of things. One of the things it checks is that you stay within your own stack. When you declare a method in Java, the compiler will compute how many items on the stack you will need. And if you look at the bytecode, it's actually encoded as part of each method. This method uses 4 elements on the stack. This one uses 10, this one uses near 0, etc., etc. And the verifier looks at the code, at the bytes of the bytecode, and it checks that you don't use the stack more than you're allowed to. This is checked before loading. It's probably not checked at runtime, or maybe it is, but it shouldn't matter. This is another one of those measures where they said, well, it's not going to be C, and you're not going to fiddle with the stack. Not on my watch. That's why they put this in. Yes, question.
If I want to append code to the beginning of an existing method, can I put it in some kind of block so that my names don't clash with names that may exist in this existing method?
So the question is, if I want to append code, can I give it some form of name that won't clash with the existing names? Well, what I usually do is use underscores and dollars, a few of them, and then it doesn't clash.
Or for example, use a block to do a try catch or something, or try finally.
A block for try finally, but it's a block in itself. I don't understand the question.
Can I do it with BCEL? Or is this, do I have to create the representation of this Java feature?
So you're saying, can I make methods that generate strings of bytecode? You're optimizing writing bytecode. So you want to make a block that generates that for you.
Yeah,
Is that?
I want to call something that might throw an exception. I want to catch the exception in my generated block.
I think I'll park that until later, because I do have some demos on exception handling. Maybe you can ask the question again then. Is that better? All right. Okay. All right. Is it because of the light? Because all the questions are here. Okay. So now I can say, oh, I'm all cool because I can write all of this in an afternoon. Well, I don't. I can tell you that. You don't write bytecode manually, because this is a lot of work. And the room for error is huge. I mean, even if you cut and paste this, you're probably going to make mistakes. It's so much, even VI will make mistakes. So what you want to do is you need something that helps you with this. And now we get back to the tool chain. So wouldn't it be nice if this was generated for us? And then we could tweak it. This is where the BCLifier comes in and the ASMifier. All right. Let me see, I made a, yeah. So inside ASM, there's a little tool that's called ASMifier. You run it on a class file. And what it generates is the code that if you compile and run it, will generate the original class. Still with me? I'll repeat that. You know, this is Inception, all right? So don't worry. They'll get an Oscar anyway. What you can do, given a class, say hello.class, if you give that to the BCLifier or the ASMifier, they will generate ASM source code that you can then compile and run, and it'll give you, again, hello.class. Okay, should I say it a third time? Will it help? I don't think so. I'll show you. All right, so we've got hello.class. And if I now take ASMifier, I think I need to feed it this. No. Some of them want the class name, other ones want the file name, and it's really confusing. I'll do it like this. I'll scroll. Bang. All right, so the ASMifier, I gave it hello.class, and it starts generating code. And what does it do? Well, it makes a little method called dump, which makes a class writer, which then, generates hello world as you would have to write it in ASM. Okay? You guys are even more quiet now. BCL first. Well, yeah, I'm sorry, I'm confusing you guys between BCL and ASM. That's the problem, is that they're reasonably interchangeable for the way I use them. Okay? So while this is actually ASM syntax for the same, you can actually read it even if it were BCL. Get static, load constant, here it is, and then the invoke virtual. The point is, you generate the code, and then you take bits of this, the part that you need, and you put that into your own code. You don't start writing bytecode as individual instructions. Do I have a BCLifier? No, I don't have that script. Sorry, that's why I showed the ASMifier, because for the BCLifier I don't have a script handy. So I didn't actually write all this. What I did, remember the workflow I presented earlier, the bootstrap process, I wrote what I wanted in Java in a special class. I decompiled that using the BCLifier, and then I copied and pasted the output into my transformer. Okay? And finally, I turn the Java class into bytes again and feed that into the JVM. It'll get loaded and it start running later on. And just to show that it works, BCL, that's the one. Compile the code, ignore the errors. Run Tomcat again. And I don't have to change the Tomcat startup because I compiled it into the same agent jar. And now you can see we instrumented using BCL. Refresh the screen. Haha. It worked. Oh. Sorry about that. Here it says I'm instrumenting this code, and then there's this throwable of the actual invocation of the close method on the pool statement. right? Same thing as we did with Java Assist, but with BCL. The difference, the main difference is that with Java Assist, I was still bound by what I can express in Java, in that string. I still have to write Java source code. And with BCL and ASM, I'm freed of what Java wants me to do. I can do whatever I like, whatever the JVM accepts or doesn't accept. All right? Any questions about this? All right, so the question is, can you use BCL to instrument BCL? To which I like to put a counter question: when? Do you want to instrument BCL as it generates the class, or do you want to have a runtime instrumentation of yourself? His answer is, I don't know. Okay, that's very relevant question. So he says, well, I'm not clear on the order of things that are happening, and when is BCL loaded? That's actually a very good question. BCL is loaded as part of the instrumentation code, so it lives inside the JVM in the agent. And what it does, all it does, it gets loaded as part of the pre-main startup sequence, and then it's only invoked every time a new class is loaded. The bytes of that class are passed to my agent, which is built upon BCL. So the actual loading of BCL happens just before the transformer is instantiated, right? Just before the pre-main method, because that class actually uses BCL. Right? Then once the code is running, once I've got a pooled object, for example, in this case, that's the example I've been using, after it's been instrumented, it has no longer any relation with BCL. BCL is only used to add instructions to the bytecode of that object, and then it lets go again. And that object goes into the verifier, into the class loader, all by itself. And it runs as though it was a normal Java class. Does that answer your question? Okay. Yes, I do. So the question is BCL loaded into the JVM before this class is run? Yes, it is. So what you do is on the command line, you specify an agent, and at that point, BCL and your agent are loaded into memory as a normal Java class. Okay? All right. Yes? BCL, yeah. Are you going to show us how you do that? All right, so the question is, you didn't write this code, or you didn't write this code. Are you going to show us how to do that? Well, the answer is, I just did, but I'm afraid I confused you a bit. So getting to this code, I'll take a few steps back, just to make clear what I'm trying to say here. If you look at this slide again, you see write in Java, compile to that class, and then decompile, right? And the decompile step, you've got a few options for. Actually, I'm switching to a different slide that has these options right there. The decompile step, you've got Java P to do actual bytecode generation, to decompile class files. But the output of Java P, you can't do anything with. You can just look at it. It's just a debugging tool. You've got ASMifier and BCLifier. ASMifier and BCLifier do the same thing except for different libraries. What they do is they generate, they still decompile a class and show it to you, but they do so in a format that you can put into your own code, so you can reuse. So these guys, in JavaP shows you the actual instructions, but ASMifier shows you, and BCLifier show you how to make a class by the example you've given.
But the code that you showed, the output for the ASMifier, was in a total different format than what you wrote in Java.
So the code that you showed in the ASMifier, you say, is in a different format. That's correct. It is because it was, and that was maybe my mistake for the organization of the talk, is it's for a different framework. If you look at the same code again, so this is again Tripwire, I know this, ASM, see, it's different again. Don't touch, paranoid, And then, this probably looks more familiar, right? Maybe I should have skipped the BCL part. So here, do the same thing again for a third time, and I won't run it, don't worry. And you don't have to applaud. But this time, this output was largely generated using the BCLifier. Little ASMifier. Oh, I'm so confused. That's the nice thing about this code. You get to have a lot of war stories and nobody really understands it. So that's another reason to do it. Now, ASM is interesting, and now I'm a bit on thin ice because I've never actually used ASM myself, right? I've always stuck with BCL because I stuck with what I knew. ASM actually has the whole, the DOM versus sex parsing, etc. They have that going on internally as well. So when you start using ASM, you need to figure out which of the two models that it supports you're going to use. So that's a bit tricky. BCL is simpler because it only has one model, which is the simple make an instruction list model, and ASM is based on a visitor pattern. And I never completely got to wrap my head around that. Maybe in the future I will. But it means there's something for you to decide which of the two models you're going to employ for your code, which is more easy for you. All right. What I would like to do now is change tack to a slightly different way of looking at this. What I want to do is I'll take a few Java classes and I'll just decompile them. I'll be using JavaP because that gives the most concise output for the actual instructions. And this should give you a feel for what Java looks on the inside, what these bytecodes looks on the inside, and how code is executed. Okay? You're free to ask as well. Within the limits of what I can do in the time, I'm happy to do a little experiment for you guys as well. Switch to my classes window. The first thing I want to show you is a bit of integer handling. So I've got, I think it's called dit. I've got a little class. It doesn't do much. It invokes a method with 4 different integers, right? A small one, a big one, 0, a massive one. So instruction-wise, this should be fairly easy to understand, because what we do is we put an integer on the stack, we put a string reference on the stack, and we invoke a method. How hard can it be? Now if I run JavaP on that, JavaP minus verbose, I use verbose to get more output, because otherwise it gets really terse. Ins.class. There you go. So this is the actual method. You can see here on the right, you can see how it invokes method 2 a couple of times. Okay? First, 555. We push, first we load, oh yeah, this is interesting. Park this one. We push an integer of 555 on the stack. This one is an instruction where the actual value that's pushed on the stack is part of the instruction. This is an optimization because it makes the instruction shorter. You don't have to go out to the constant pool or anywhere else. You just have an instruction that says push an integer, and this is the value. And it's all in the same 32, maybe 64 bytes. Then we load a constant reference from the pool, and we invoke our virtual method, which is method 2. Now method 2, if you look at the Java code, method 2 takes 2 arguments, right? An integer and a string. But if I look at the stack, it loads something magical, then we've got the int, and then we've got the string. What's this? You can guess? Ah, wow. Thank you for the joke. This, indeed, this. This is this. Yes, this is the this pointer, right? What actually happens is you think you call object.foo, but in reality it calls foo from object with an object, with the actual object reference as the first argument. So underwater, all the compiler does is move that thing you put before the dot and put it behind the brackets.
That's exactly like invoke method.
It's at the end of the day, this is an invoke method. Yeah, it's a bit more involved. Here you can also see things are typed again. A, which obviously stands for object. And not for array. I don't know. Now, pushing 0 onto the stack, I don't know about you guys, but if I look at my code and I were to remove all the zeros, there's a lot of them. So much so, in fact, that there is a special instruction, which is even shorter, to put the value of 0 on the stack as an integer, not a byte, mind. Then we load a constant, invoke virtual. So you can see that between 555 and 0, there's actually a difference in how that value makes it onto the stack, and optimization even. And then we've got the byte to integer push. So this is actually a byte value that's being pushed on the stack and then expanded to an integer. Ooh, another optimization, because this one is also short, because the actual value is a byte, because it fits in a byte. A lot of fun that compiler must be. I mean, it's all day, it's like, oh, wait, I can save 1 byte here, and then somebody loads Hibernate, you know. Jeez. Anyway, load constant, sorry, had to say it. Load constant, if it's big, if it's a big integer, you know, there are not a lot of them. And then by the time if you're working with these big numbers, they'll be put in a constant pool. So here you can see that 4 lines of code that to my eyes are identical are actually under the covers are handled completely different by the JVM, right? It's still all typed, but it makes a really big difference whether you push 0, 12, or 555. Or 1,000,000. Well, it's 1 billion more. All right, and we've seen the this pointer. Anything else? Let's see what I've got. Yeah. Yes, question, 2 even. The question is there a reason constants aren't typed in the bytecode? But they are. Allow me to show. I push. Load constant. Let's see, reference to 21. Let's see, 21. Integer. It is typed. Okay. Yeah. That's a good question. I don't know. So this is typed. The question is, does the verifier then check the type? In this case, it can, because it is in the content pool. Yeah, so it has all the typing information. So my guess, and I have to admit it's a guess, would be that it's still the verifier can check that the typing is correct. There was the person with the blue shirt was first. So the question is, if you were to write this manually, would you have to respect precisely this way of handling these integers? The answer is no, as long as you stay within what is acceptable for that. I mean, I could load everything using LDC and take it from the constant pool, which would be the most generic way of handling, but not necessarily the most performant way. Okay? You have to respect the typing because of the verifier, because otherwise your code won't load, but you're free to not use these optimizations. Yes? Go back to the constant pool. Yes, sir. 15 is a string. I'm not quite sure, but you can see that there is an indirection there. The actual string is number 16. So probably what is the string encapsulates an array of UTF-8 bytes or something like that, or UTF-8 characters or something like that. I'm not quite sure what's happening here. Yes, question. Method. Cool, huh? We code by proxy. This. So the question was, why are we jumping through lines? Whereas somebody else in the audience comments, well, that's the size of the bytecode. So you should be able to see the optimization here as well. You see a load 0 is actually a small instruction. This one is longer. See, 3, here we increment by 3. And this one, we do a load and then a constant, and it's all incremented by 1. So here you can indeed see that it's on disk, it's shorter. We saved all of 3 bytes there. Cool, huh? Any other questions? Maybe on the right. Maybe I speak too much to this audience. Yes, sir. So the question is, will this be aligned for efficient execution on whatever processor you are? My guess is that it will be, because these guys do performance for a living. But there's no guarantee, or even, I don't think the specification demands that it is. But real world will probably demand it is. But, and there was a question from JFall actually, there's probably a very close mapping to what actually happens on a machine. But you've got to remember that this stuff isn't executed as is. This is actually passed into hotspot before execution. So this is compiled again before it ever hits the machine. And maybe hotspot decides to do one-on-one mapping, aligned or not, or maybe it decides, oh, I can do much better, and it does something completely different. You and I don't know at this point. Okay? All right. Let's do one more. Let's see what we have. So we do exceptions. We've done inception, exception. Anyway, more throw exception.java. So what I wanted to do with this, and it's a bit hard to read, sorry for that. What I wanted to do with this is play a bit with exception handling, just to see what's being generated under the hood. And when I do stuff like that, you can see that I use a lot of what I call marker code things. That is a predictable piece of code that I can easily recognize in a stream of bytecode. And that allows me to say, all right, this is the boundary of Java code from here to there. Right? So I put a lot of these in, not because I am interested in executing this or seeing the output, but because it allows me in the bytecode to easily recognize some of the patterns. So what we do here is marker 1 is before any try catch. Then we've got the try block where we invoke bar, and we catch an IO exception of which we print the stack trace. So foo is really a using method that does a try block for IO exception. Then we've got the bar method, which with a little bit of help of the compiler manages to throw an IO exception. So bar throws the method, foo catches it. Let's have a look at the bytecode. Boom. What do we look first? The throwing or the catching? What do you want? Throwing. See? So that's the bar method, right? That's the one that throws the exception. Here we see that the exception is actually declared as part of the signature. Still at this level, right? Machine code guys. In machine code, you don't have exceptions anymore. The JVM is aware of exceptions. It knows how to handle exceptions. That's very interesting because that makes it fairly safe. You don't have to do jump tables or manually have the compiler generate that. Yes, there's a question. Oh.
Technically, the throws here is only for the compiler, not for the VM. The VM don't care about the exception you declare.
Okay, so the point you're making is technically the JVM doesn't care about what you declare here. This is only for the compiler. But the information is present in the bytecode. I might touch it, fiddle with it. Okay, good point. So the verifier doesn't actually verify it, you're saying. That's interesting. All right, so what it does, here's the marker code, yeah? Those 3 lines, get static, load constant, invoke virtual. That allows me to recognize this very easily. Get static, another marker. And then we do new IO exception, duplicate it, and then we've got the string, and we initialize, right? Remember, exceptions are objects in Java. You say new, and you do, that's an actual constructor. An exception, even at this level, is a normal Java object. And for the people who use machine code engineering, this is actually, the JVM has instructions to do object handling. It has a new instruction. And then finally, a throw. A for object. Sorry, but not? AU? Your point is not a new. Yeah, I guess they thought it was implicit that you don't do new on atomics. Sorry, on inch. Okay, so let's look at the catching code. This is the foo method, right? That's the one that's going to be on the receiving end of this. So here we've got, again, the marker code. The marker before invoking bar. You see that the actual try bit doesn't generate or seem to generate any actual bytecode here. We call this dot bar, or actually we call bar with this. And then after invoking bar, go to, yeah, it's there. I actually missed it. That's one of the reasons I went to bytecode engineering. We go to line 44, which is the return, or here we have the exception handler. So we have here you can see the catch block, where you actually jump over the catch block if nothing is wrong. And then, where is it? Where are you? Just local variable table. Then there's this. No, that's the... Sorry, what? One line up. Exception, thank you. Glad you guys can actually read it. So what it says here is that in this piece of code from line 8 to 28, if there is an IO exception, you jump to line 31. So what happens if I invoke a method and it throws an exception, what was it, 8 to 28, jump to 31. Okay, so 8, that's the marker before invoking bar. So that's the try thing, it was just above that. To 28, that's the go-to. So if between these, in this block, an IO exception happens, then you've got to jump to line 31. Right, is this clear? This is exception handling as the JVM does it. Okay. Anything else? So this one. There's a store. That's a good point, actually. So something is stored at this point. I don't know. What is stored? Does anybody know? Do you know? Won't you join me? The actual exception. Because it's needed when you return. No?
Magically, the VM put the exception on stack.
Okay, so when the bar method is invoked and an exception is thrown, I can find the actual exception on stack. That's what you're saying, magically. So then I now store the exception. Okay. So here what I do is I store the actual exception, which I can then load and call print stack trace on. That is your point. Cool. I learn a little every day. All right, did everybody get that? So what happens is the bar method doesn't return the exception. Where does it go? Instead, what the JVM does, it pushes it onto the stack, where I can find it, which you can just put in a local variable, and then I can use that local variable later on to actually do the exception handling.
I think it only happens because you do a print statement before.
So you're saying it only happens because I do a print statement before? I don't know.
It says load constant on 35.
Let's find out. So if I remove, you're saying that if I remove this print statement, it shouldn't have to store and load it, right? I did? I don't think I did. Right, so the storing, the magical push onto the stack and store it thing happens here, right? So I removed the print statement. There should be no need to store it. Yes, I still use it, but you can use it, leave it on the stack, because I use it on the stack. It doesn't work like that. All right. I'll compile it anyway, just to be pedantic. Throw Java. So the idiom is still there, except there's no reason to do it at this point. But that doesn't mean that this is what gets executed. I mean, Hotspot will probably see this and remove it. Yes. Sorry?
There is a really good reason to do that.
Okay.
Which is something which is really, really important, which is when you generate bytecode, you talk to the VM, and the VM only recognizes some patterns. So if you want to generate bytecodes, you have to generate these stupid codes. Because if you generate optimized bytecodes, the JIT will not be able to optimize it.
Okay. So your point is you've got to do this to make it clear to the JVM what it is that you want to do, because otherwise the JIT won't be able to see the pattern and optimize it. It'll say, hey, I don't recognize this pattern, so I cannot optimize this code. Aha. Thank you. Interesting. They should give you a mic. All right. Any other questions about this? Yes.
So if the exception is thrown, the stack grows in a way. If it's not thrown, the stack grows in another way, right?
So you're
When I think about the max stack size,
yeah.
which one should I consider? I would imagine that like I should consider both and then take the biggest one.
So the question is, if I have an exception, I have one use of the stack. It grows in a certain way. If I have no exception, the stack is used in a different way and may grow in different patterns. So which of those two uses I should set max stack to? Well, the max stack is actually for the execution of that method, regardless of whether exceptions happen or not. So they need to, it needs to be the biggest uses of the two. Okay, but if you look at ASM and BCL, what they allow you to do is you can say, make the stack what it needs to be. And then the frameworks, the tools will make the stack and set the size for you without your interference. So you don't have to go and count bytecodes on the stack. You can just have the code, work, which is nice. And is a lot less prone to error. Yes, question? So what happens if you don't do anything with the exception at all? So you have an empty catch block. You want me to do the code? I mean, it's easiest. The compiler is really good at answering these questions. So there you go. All right, I removed it, compile it, decompile it. Go to 32. It just stores it in a local variable. So it doesn't take it out again. This is the minimal catch block. Okay? All right, let's go to the next one. So what I do here is, what I want to do is just create a bunch of method invocations that are different in some way. Some have arguments, some are static, just to get a feel for how these things are called, what instructions are used to invoke these methods. Let me find the main method first. I should have added the static block as well, shouldn't I? So this is the main method. And what we see here is we make a new instance of methods on which we invoke the constructor. And here's that interesting store load twiddle again. And then we do a invoke virtual of it. Okay, so then we have the dis pointer on the stack. Yes, question. So why is it duplicated here on line 3? When I do new, it leaves one reference to the new object on the stack. If I invoke init on it, a method invocation will take the method reference off the stack, and it's gone. So that's why I duplicate it. I've got two references to the same method, and then the init takes the first off, and the foo takes the second off. All right, so this is a normal object, a method on an object invocation. So here we do foo, which invokes bar, and you can see this pointer being loaded, invoke virtual, nothing new there. And here we push, with this pointer, we push 12 onto the stack, pass in an argument. And as we have baz, which takes an argument, doesn't do anything. All it does is return. An important one here is missing is the invoke dynamic, which I really don't know how to do from Java code, so you probably have to decompile one of the languages that actually use it to get at that. Okay? The point here is that you've got different ways of invoking methods. These are all invoke virtual. If I take, methods.java, if I make this one static,
Can you make it private as well? Does it matter?
I can make it private. Private static void baz. Methods.java. So now Baz is private. It looks like it's been optimized away. That doesn't help. Damn optimizer. Oh. Just something in there to avoid it getting deleted. Don't get helpful with me, optimizer. So let's find the Baz method, which is the one that we changed. It's here. No.
By default, JavaP doesn't show private method. You have to
Okay. Dash private, thank you. There you go, thank you. So by default, I'm told JavaP doesn't show private methods. You have to add minus private. Nice. So here you've got your private method, which is static. And you can see that instead of using invoke virtual, which was used for invoking normal methods, it now uses invoke static. So it has a separate instruction to invoke static. Yes, question, don't get you.
How does it look if you call a synchronized method?
Synchronized method. Ooh. Methods was called, huh? Which one should we make synchronized? How about bar? You need to help me with spelling because I always do it wrong. Like this, right? Thank you. See? Yes? Java C. Bar. That's it. Sorry, what? It has a flag, yeah, which tells the JVM that this is something we want to invoke synchronized way. Okay?
There's a difference between a method that's synchronized and a synchronized block and explicit one. Because I guess then it's not enough to just do it like
Synchronized. Yes, this is what you expect, yeah?
I expected this to be the same as a method.
Nope. It may have the same effect. It's not quite the same code. Scope is different. That's a good point. The scope is different. I think the gentleman on the stairs was first, then I'll get to you.
You mentioned that you don't know how to generate invoke dynamic in Java.
Okay, yes, I did.
Create a lambda with Java 8, it will create an invoke dynamic.
Okay. So,
Version of a lambda use invoke dynamic.
right. So if I were to install, thank you for that. If I said I couldn't generate invoke dynamic, but Java 8 lambdas actually use dynamic invocations, which I can't show because I don't have Java 8 on my machine. So sorry about that. Thank you. One moment. Yes?
Is there some case where the Java compiler inline some private methods or static methods for optimizing? And if it's not the case for private and static methods, is this the case for lambda in Java 8?
Okay. I can't answer the question, but I'll repeat it anyway. So the question is, does the compiler inline private static methods and does it do the same for lambdas in Java 8? I have to admit I haven't looked at lambdas yet, so there's some room for me to learn. I don't know. I don't think the compiler does all that optimization because that role is for Hotspot to do, right? So for the JIT compiler. So I'm not sure it does any inlining, but really I don't expect it to do because there's so much going on inside Hotspot. It probably wants, you know, if I take what we've seen earlier about the store that was explicit, the store and load, I think the hotspot actually would want to have that information to be able to do better optimizations. Okay? So there are 2 monitor exits here, and there's a go-to.
And there's a throw behind below the.
Yeah.
So that's something with exception.
So there's something exception handling going on. I don't know. Yeah. Oh, yeah. Yes.
Basically, the way synchronizing is implemented is like a try-finally. I don't know if you have an example with try-finally.
Okay, so you're saying that the synchronization is actually implemented in the form of a try finally, hence this idiom. Okay, well, I can make a try finally. I mean, we're here. Let's make a try finally. So, try it. Sorry. All right. So we had this idiom where there would be a go-to, which you remember from the exception handling. And now here we have the same go-to. So finally the monitor exit, where is it? Oh, I'm so lost. I'm too high. So the monitor exit is actually called inside a finally block that's been generated for us. Is that what you're saying?
The idea is you have 2 possible paths. One is there is no exception which is thrown.
Yes.
In case you have the first monitor exit. And
Yeah.
if an exception is thrown, you have the second.
Okay.
You can see it on the exception table.
That's below. Yeah. Oh, yes. I was wondering because I saw exception scopes being generated that I didn't understand. So, as the gentleman was saying, not only am I coding by proxy, I'm also presenting by proxy. It's a try finally block that's being generated for the synchronized block. And as with try finally, you've got 2 code paths. You've got the happy case where the first invocation of monitor exit comes from. And then if there's an exception, this one is actually being used to the same effect. Okay. Oh yes, sorry. Black on black is quite hard to see.
If you have an operation that is
I seem to have talked so much that the battery was down. All right. So the question is, I've got a method that should return an integer, leaving it on the stack. Where is actually checked that the exception is if an exception is thrown, which wouldn't leave an exception integer on the stack, but would leave an exception on the stack, right? The exceptions are actually part of the JVM execution path, so it's not shown in the bytecode. What you actually do is you can assume that the method, if it returns, leaves the integer on the stack, as expected. It's just that if an exception happens, that next instruction is never executed. What? The one that expected the integer is never executed. Instead, the JVM consults the exception table, and it says, all right, we're not going to the next instruction, we're going to whatever the exception table tells us to go to. Right? So that's how we can avoid, we can just assume that there'll be an integer afterwards. We don't have to go and, oh, if there was an exception on the stack, then we do this. That would be nasty. Yes, another question. Yes. So if we're here, that's a good point actually. So if we couldn't exit the monitor, we try again. I don't know, maybe this is a spin lock? I don't know. If we couldn't unlock it, this is where we are. That makes kind of sense. I mean, you can't leave this code with the monitor still locked. So you need to be able to properly exit the lock. So I don't know. This might be a just in case bit of code. Or maybe, I don't know about the monitor actually, maybe there is a good reason it might fail and you have to try again. And then you have a simple implementation of a spin lock. Very good catch. I never saw that. Thank you. All right, where do we go now? This is one, I don't know if you guys have watched Joshua Block with his Java puzzlers. This is one of the Java puzzlers where you have a return in a finally, and the question is, what does the method return? Return in finally.java. Let's look at the Java code first. Sorry, could you repeat the question? So the question is why the compiler doesn't forbid it. Well, I don't know about that one. I'm not into politics. I think you guys need to put it outside. All right. So let me review the code here because there's more than I expected. So what I've done here is I've constructed a bunch of different forms of try finally with the idea to just explore what it looks like. So I've got, above here I've got a simple finally, which is just a try finally, which we've already seen. And then there's a catch with a finally. And then what we do here is we've got a return in a finally. And then we return a local variable in a finally, just to explore that. Okay? So what I've done is I've got 4 methods, each with different ways of handling local variables, return values, and exceptions. Return infinite.class. And there's a lot of code. The whole rule of keeping your code on one screen is a bit problematic when you're doing this kind of stuff. All right, simple try finally, okay? And this is mainly all marker code with a few go-tos. What you do see almost immediately is that the finally body is actually referenced twice. There is an exception handling table, but we do, let me see. So here you've got the original try body, which consists of this, after which we jump to line 22, which is the actual finally body, and we execute the finally. So this is the happy flow, where you have your method body and you have got the finally body separate. If an exception had, actually no, there's nothing else. We don't have an exception handler here. So it seems that here there is a just in case. Wait, if an exception handling happens inside the body, so imagine we don't throw an exception, but we call a method which throws an exception. Then we go to this code by the exception table that's down here. It says if something happens, we go to line 11, where we store the actual exception, which I've just learned, thank you. And then we do the finally body, which is the marker code. And then we rethrow the exception. So here you can see what happens if I'm in a finally body and an exception sort of passes by. We actually execute the finally properly. And you can see that what it does, it generates a second instance of the finally body to be executed, and then to leave, to end with throwing an exception to whoever called us. If we move on to the simple catch finally, where we do have a finally catch body, there you can see we do the try body, catch body, and then again finally body for each of the code paths. Now we have 3 code paths. One is everything went right. One is there was an exception. One is there was an exception that we knew how to handle. And the compilers generated a finally body for each and just generated a code for each. Doesn't factor this out. All right, now we get to the returning of values thing. Any questions so far about the try finally? Yes. So the question is, what was the type that we were catching in the catch block? I'm not sure, actually. Return to Java. It's actually throwable. So why would you generate anything but, why would you generate the extra case? Because if it's throwable, it should end up here anyway. What I think is happening is that the compiler just has these idioms it will generate, and it doesn't try to optimize at this stage and reduce the code. And that's a bit funny. I mean, at a bytecode level, it's like, oh, here we can use 2 bytes instead of 3. And then here we say, oh, generate 4 catch blocks, or 4 finally blocks. I'm sure there's a good reason. It's a lot simpler to write, and you shouldn't catch throwable anyway, to be honest. Oh, should I say that? Anyway, returning values. So now we go to returning finally, which should be this code, yeah. So now we've got a return in finally. Finally body is here. And here what you see, if you look at what it does, it just hard returns the value of 3. And if you look at the happy flow, what it does, it goes to line 24, executes the finally body, and then ends up returning 3. If you look at the actual code, just to remember it, you'll see that here's a return 1 and a return 2. And they are missing from the code that was generated. Let me find it back. No, that's the local one. This is the return finally. And here you can see that the only return is at the end, which returns a value. I return the value of 3. And I return the values of 2 and 1 are suppressed. The compiler seems to have figured out that it can't return those values. If we do the same with the local variable, so we don't use constant as we did before, we use a local variable. Here we see we store the integer, go to line 52, and in the finally body, we do the return again. But now we do see that it does, let me see, go to 62. So now you see that in each of the finally bodies it generates, it stores the value. Yeah, that's better. All right. So here you see that it does store the values in the finally bodies and doesn't suppress them. Any questions about this? I told you you'd start sleeping as soon as you get to the actual bytecode. Okay? 2 questions I see. Right, so your question is, if you put a lot of code in a finally body, all of it gets duplicated. I think the answer should be yes, but I see...
You can do a try finale in a try finale. In that case, you will have all the possible cases.
Right. So your point is, your question was, will all of it be duplicated? And your answer to that is try finally nested inside the finally block, and you'll see that every single code path gets its own instant of all the code in your finally block. Another thing to remember is that these are bytes codes. Yeah? You're looking at 20 bytes worth of stuff that's being duplicated. On a scale of loading Tomcat, Glassfish, or JBoss, nobody will notice. Honestly, nobody will notice. There was another question, yes? Sorry, can you use? Yes. So the question is, can you throw something that's not throwable? I got the question before, and they were asking if you could throw sheep. Let me see if the... I think it's this one. So, BCL. Let's make an object of type sheep. Let's see where I need to... sorry, I need to see where the actual code is. Sheep. Natuurlijk. So here you've got a little code, a little piece of code that tries to throw a sheep. And what we do, remember the workflow, we try to express as much as we can in Java before we go to the bytecode level. So here what I do is I have a method that throws a sheep, right? Or I try to throw a sheep. First I make a sheep instance, which I'll need, like an exception, and then I do throw new exception. And what I'll do later in the bytecode is I'll take that new exception and replace that with throwing the actual sheep, which I've created earlier. So then, using BCL and the BCLifier, I turn this into bytecode, which I've named sheepCreator.java, which was generated for me. Okay? So this is the original class, and probably from the demo last time I did it, the change is already there. So here, let me see, I do an init on sheep. So what I do there is I create a new sheep. Where is it? Where is it? I lost my code. Is it this one? Yes. Here we go. All right. Just for the demo's sake, I'll remove the comments. So this is the create method 1. This is the one that attempts to throw the sheep, right? Here we see we create a new sheep, which we duplicate for the constructor. We store it. And then in this case, what we do is we create a new exception, which we then duplicate and give it the bar argument, and then construct, and then finally throw it. Oh, sorry, this one. Throw it, right? So what we do here is we create a sheep, which we then ignore. We create a new exception, which we then throw. Now the exception is throwable, the sheep is not. So what if I don't store it, but instead, am I doing this right? This is the tricky part, because do I do that store or not? So here, I make a sheep, I duplicate it, I construct it, I do the constructor, and then I throw it, right? I've commented out these 5 lines that were constructing the exception for me. Is this clear?
Comment out the last line,
Sorry, did I comment?
the one below. Can you comment that out? No, the type string, or it's just wait.
No, that's just wrapped. Sorry, yeah. So yeah, the string, sorry about the screen width. Okay, so instead of making a sheep throw an exception, I'm making a sheep and then throwing it. Java C min D. I did something wrong. What did I do wrong? Oh, wait. I need Java BCL, obviously. Come on, guys. You could have helped me with that. Workspace. Tripwire. Where did I leave the library? BCL. Okay. Remember reception. So what I've done, I've generated a class that can generate classes. I've changed what it would output, and now I've compiled that, and if I run this one, it should leave me a class that I can run. Java sheep creator. And I do need BCL for this. What did I do wrong? Oh yeah, it's minus CP. Sorry. Now what? Try it the other way around. Yes, no. Guys, I need some help here. I'm making all these errors and you're not correcting me. Okay, after a bit of fiddling, I compiled the class and I've ran it, and it should leave me with a new sheep.class, which, if I look at the clock on my machine, tells me this is a new thing, sheep.class. Java -d sheep.class, sheep, -d dot. Notice at this point I no longer need BCL. That was the question of the gentleman in the white shirt. So once the class has been instrumented, BCL is no longer needed, because this is just a regular class, except it's been fiddled with. Let's run this, see what happens. Now. The answer is no, you can't throw sheep. So here, the verifier kicks in and says, no, that's not good. All right? We did our best. Now, the verifier is not a very useful thing. This is reasonable. I've worked with all the JVMs, and the verifier, it was designed for catching edge cases. So normal people like you and me don't have to look at the error messages. So it's not always very clear. And one of the things that the guys from ASM did was add their own verifier that you can run, and then you can get more detail on errors than the JVM will give you. So there should be a script that I made for that. And it's called, for some reason, check class adapter. That's the name of the thing that's part of ASM. Let's have it verify. Oh, sorry, that class. No. What am I doing wrong? Is that class path missing? Okay, demo effect. Sorry, guys. It's supposed to bitch about the fact that this sheep is not correct, and but it doesn't. Not today. So we'll have to make do with what the JVM thinks of this. But this one is reasonably clear, can only throw throwable objects, which a sheep is not. Yes, question after that. All right, so the question is, can you trick the verifier by having a code path where you either put a throwable or a sheep onto the stack? That's an interesting one. Probably not, mind, but
You will have trouble to generate a stack map, stack frame map.
oh, you're saying you can't generate that code because you have trouble generating the stack map. It won't, yeah. But the stack map was introduced in the newer JVMs, right? You can switch off the verifier to have that.
Yes, but in that case, the verifier follow all the passes.
Ah, okay. So it'll just explore all the code and it'll check that, it'll find this trick. That's what you're saying. How do you know, if I may ask?
I am one of the developers of ESM.
Ah, okay. Nice to have you. All right, good. All right, so the question is, can I trick the verifier? And the answer is probably not, right? It was designed not to be tricked.
But you can do something.
Sorry, you're speaking ahead of time. Well, the question is, can we replace the verifier? And how can we replace it? Well, like I said earlier in the talk, there are actually, right now, there are two verifiers in your JVM, in the newer ones. So you've got the new verifier and the old one, which you can switch between the two, as I shown you earlier. Replacing the actual verifier in a JVM is a bit tricky, but you can compile your own JVM and have your own verifier in there. There's no programmatic access to that verifier. It's part of the core of the JVM. It's not something you and I from Java code can touch, even from bytecode. Okay? Yes?
You can do the path where you try to throw a sheep, but you make a variable object where you just put in a sheep or an exception, but you have to, before throwing it, you have to cast it to throwable again. So we just get a class cat exception on throwing.
Right, so your point was you might write the code, but you would end up having a class cast exception as you try to cast a sheep to a throwable before you want to throw it. Yeah.
You don't need DCL or anything, you can use it in Java code.
Right, you would pass the verifier, it would say yes, fine, whatever, but you would get a runtime exception instead of a load time exception. Good point, thanks. Yes?
There is something that you can do is use dash no verify when you execute Java.
Oh, cool. No verify. Yeah? Ah, it loads. All right, so usually, yeah, this one doesn't have a main method, so I can't demonstrate that. But I'm told the JIT will crash. So, okay. No verify. All right, that also answers your question. You can replace the verifier by nothing. It's going to be hard to get whoever uses your program to switch that off, though. But, you know, a GIF of somebody who's very important and very good-looking usually helps, and then you can replace the JVM with one that doesn't have a verifier. Take it from there. Yes?
With exceptions and runtime exceptions, is the constraint that the method can only throw an exception that it declares in the part of the virtual machine or part of the compiler? So could I create, with bytecode manipulation, a method that declares to throw IO exception, but in reality throws a class cast exception?
So the question is, can I, if I declare a method to throw one thing, like a IO exception, can I then throw something that's not declared? I think the answer is going to be yes, you can probably do it, because I was told early in the talk that it's not actually checked. But we can try it. How's about that? So we can reuse this sheep creator.java. And again, it doesn't have a main method, so it can only show you that it passes verification, right? Which means it'll run. And what I can do, actually, I don't have to do anything. If you look at the way this method is generated, it doesn't declare any exception, yet we do throw exceptions, right? So at this level already, the information, what is declared on the signature of this method is not available. We actually generate this method without. So this shows that the answer to your question is, yes, you can throw anything. And the JVM will go up the stack of method calls and find one that can handle that particular method. Yes?
I think even you can, using reflection, throw a checked exception from a method that doesn't declare anything.
Right, so your point is using reflection, you can throw a checked exception from a method that, yeah. Well, there's also a project Coin which had a sneaky throw, which in Java, even without resorting to bytecode, you can throw checked exception without them being declared. And there's no reflection involved, actually. Okay. Any last experiments? Yes. 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 So if I were to write code with a loop that leaves integers on the stack and then invokes a method that needs a string, for example. Yeah. Yeah, so the question is, if I leave a bunch of integers, make a for loop that leaves integers on the stack, doesn't take them off again, and then and then I invoke a method that needs a string. I think, without trying it, I think the verifier will actually catch that, because it's pretty easy to see that, oh, at this point I need a string, and it can go back up the code and say, hey, look, does anyone leave that string for me on the stack? And it doesn't, because there's some code that does a lot of stuff, but leaves only integers. So I think the verifier will actually explore that and find the problem. So what you're saying is that here, for example, the init, I put the I push the string onto the stack. Let's see if I can do this live coding. This is very tricky because I'll probably make many mistakes. No, I'm not going to do the experiment, sorry. The way the instructions are laid out is that it's very easy for the verifier to actually check. It can just go back and say, all right, what is on the stack at this point? Because it can explore all the code paths. And I don't think there'll be a situation where you can put the wrong value on the stack and the verifier will miss it. Right. So you're saying that if you make it in somehow conditional, the verifier won't be able to execute the code and just determine what's on the stack. Yeah. I don't know. I don't know if that's possible, actually. Sorry. So your point is in response to that gentleman saying, well, if you make a loop, then at the end of the loop, it should have cleaned up the stack again. If you use bytecode manipulation, you can decide not to clean up the stack, right? So you can do essentially whatever you like. It's up to verifier to catch those situations. I think it will catch those situations, in all honesty, because of the way the instructions are constructed. So the question is, does the verifier give an error if you don't clean up the stack in that local block? Well, the verifier doesn't actually recognize the blocks. What it sees is a bunch of instructions that are part of a method, and at the end of the method, it'll just throw away the stack. So it doesn't care whether you leave stuff on the stack or not. It's just ignored. As long as you don't exceed the limit that you have, you're fine. The blocks, so the scope blocks that we see, are present because they are scope tables, but they're not actually used for this kind of stuff. Sorry, there was a, yeah? All right. So your point is, if the verifier doesn't know how often a loop is executed, or in this case a jump is executed, how can it check? Good point. I don't know. I'll tell you what. I've been live coding some of this stuff for you guys. But my purpose was to get you guys started using this. So maybe this is an experiment that you should try, based on you're happy to have my code, and you can try it for yourself and see if you can trick the verifier. All right, one last question, then I'll move on. Oh, two last questions. When do you use this kind of tricks? Well, like I said, you don't. You do this if you're writing really tricky library code. I mean, imagine you're rewriting Terracotta, or you're doing JRebel again, or you're writing your own profiler, or like me, you need to have that one method invocation on that one object that you need to know. That's when you resort to this kind of stuff, either because your boss asked you or because you're interested. Most people will actually do this because they would like to know how to trick the verifier. Okay?
I wonder, there's a tool that comes as a visual VM plugin. It's called btrace. I don't know if you've ever heard of it.
I haven't heard of it. Okay.
btrace only for running bytecode.
Okay.
If you haven't heard of it, then my question is kind of funny.
All right, so the question, which doesn't really turn out as a question now, is there's a tool called btrace, which is supposed to be like dtrace, but for bytecode. Like I said, I have no experience with btrace or dtrace for that matter, so I can't answer your question there. All right, so I would like to wrap up with a few last remarks. So when you start doing this bytecode, make sure you look at your tool chain, make sure you look at the process that you're using, and then it's actually quite fun. And if you have questions like the ones that I've been unable to answer for some of the people here, you can do the experiment yourself quite easily. This is really, tinkering, make sure you're alone, nobody's bugging you, make sure you have plenty of coffee, and it's a lot of fun to do. So on the decompilation part, you need JavaP at least, you need the asmplier, and there's actually a good thing in Eclipse. There is a bytecode plugin. So I've been bugging you guys with the command line, but there's actually a plugin for Eclipse, which can show you the bytecode of any given class. I'll make this slightly larger. Sorry for the font size. But what it does, it allows you to go to any method, click in it, and it'll show you the bytecode for that method, right? So the whole JavaP thing, I've been using it, like I said, because it's always there, and this is something you may or may not have. You may or may not use Eclipse. But this shows you what JavaP showed you earlier, but for whatever code you happen to be editing at the time, which is a very nice touch. It comes with the documentation plugin as well, so a documentation view, which gives you per bytecode, per instruction, gives you the usage and the definition of it, which is very instructive if you're trying to figure out how to bypass the verifier, for example. That's the verifier, for example. And on the debug part, well, you don't have a lot of tools. You've got the verifier, and obviously println is your friend. And you should check out, hopefully better than me, the ASM class adapter. And when you're stuck, remember this. Thank you for your time. Any last questions? Yes, sir. A working agent example. Using the attach API. No, I don't. Sorry. Yeah, I don't. There is a way where you can runtime attach code to the JVM. I haven't dabbled with it. Sorry. No, like I said, I haven't tried it out, but maybe we can give a talk on it. It would be a good reason to experiment with it. Yeah, so the point though is the instrumentation API is, I've shown you this much of an API that's this big, yeah? So make sure you read about it and explore it and discover all the wonderful things that are in there. All right, thank you very much.